So section 8.3 of the textbook is going to cover a shape called a hyperbola, and this one's going to have a lot in common with the last one we were looking at, the ellipses. The most challenging thing about this section is how similar the two shapes are. It's very difficult to keep track of the slight differences between their equations and formulas. So for an ellipse, I told you that it is defined as the set of all the points whose distances from the two foci had a constant sum, which means if you added the two lengths from the point to each foci, it always equal to the same number. For this, it's very similar, but instead of it having the same sum, it's the same difference, which means if you subtract the distance to each of the foci, it's always going to be the same number for any point along this hyperbola shape. You'll notice that we have a lot of the same terms that we had for an ellipse. We still have a center, we still have two vertices, and we still have two foci. The big difference for this shape is that now, instead of having the foci on the inside next to the center, now they're on the outside. So what's happening is the graph always kind of gives like a protective layer around the foci or foci, but now that those are on the outside, that means that now the graph is going to go away from the center. So for an ellipse, the foci are on the inside and the graph wraps around them. For the hyperbola, the foci are on the outside, so the graph points away from the center. Here you can see the standard form for the two different versions. There's the version where the graph opens to the left or to the right, so you would have something going in opposite directions this way. And then here's what it looks like when the hyperbola is instead opening up and down. If you didn't look carefully, you might have thought this was the exact same formula we just had for an ellipse. The difference is this symbol right here. It's that it's no longer an addition symbol, you're now working with subtraction. So that is in fact what causes the difference between an ellipse and hyperbola, and it's why the shapes seem to have so much in common. They do have a lot of the same variables inside of them. Here's another important difference. When you are trying to find the foci for an ellipse, the formula was that a squared equals b squared plus c squared. Now I'm giving you a different one. Please do be careful about noting the difference. This one actually is that Pythagorean theorem you guys are more familiar with. So a squared plus b squared will equal c squared. You're going to need to use this formula anytime you're dealing with anything related to the foci, or if you're trying to go backwards from the foci to the standard form of the equation. You'll have to use this to find the missing a, b, or c value. This graph actually does have asymptotes, and we'll be using the a and the b lengths, which are the numbers that you see underneath in the denominators for a hyperbola, to create those asymptotes. We're actually going to draw a rectangular box using the lengths a and b, and then when you draw lines going through the corners of the boxes, that will make the asymptotes that your graph approaches but never touches. And something else that's kind of annoying about the difference between an ellipse and a hyperbola, for the ellipse, we had something called the major axis and the minor axis. And we had the lengths 2a and 2b. We still have those lengths, 2a and 2b. It's just that for a hyperbola, we have different names for them. So the transverse axis is going to use the same variables and be solved for the same way that the major axis was for an ellipse. And for the 2b value, for the ellipse, we called it the minor axis. Now it's going to be called the conjugate axis. So that's just one of those things that's annoying. It's hard to keep straight the different terms for the different shapes. So you will need to memorize that either the major axis or the transverse axis, depending on what shape you have, is the length of 2a, and the minor axis will be the length of 2b. Going back to our shape after having looked at those terms, so let me show you again that the distance from the center to the focus, either of the foci that you have, that will be the length of c. And if you were going from the center to the vertex, to where the end of the hyperbola actually crosses through your axis, that's the length of a. And so this time we have that our a value is shorter than our length for c. That was different the other way around because, again, it's because the vertices and the foci have switched locations. Now the foci are on the outside, so that is the longer distance for this shape. So here's our first most common example, very similar to what we did for an ellipse. Sometimes they're just going to ask you to get it in the standard form so that you can readily identify some of the terms like the vertices and the foci. Just like with the ellipse, the first requirement, this has to be set equal to 1. So if you have a different number there, like in this case 36, then you need to divide everything by 36 so that on the one side of the equation, all you have is equals 1. So 4 over 36, if you reduce this, this will end up being x squared over 9. And then again, to emphasize, this is a minus symbol now, not a plus. That's what makes it a hyperbola instead of an ellipse. And then y squared. If you reduce the fraction 9 over 36, now we have 4 in the bottom. And as required, we now have it set equal to 1. So from here, we can go through and we can list all of the different variables and everything we have. I don't see a number being added or subtracted from x, which means h is 0. I don't see a number being added or subtracted from y, which means k is 0. And for a hyperbola, if you look back at the formulas on the previous slide, for this shape, a squared is always the first denominator. Now the order does matter because we're no longer adding two fractions together. So a is always going to be the first denominator. It's going to be the one that has a positive coefficient out front. So whether x or y is positive, it's whichever one is positive that has a squared underneath it. So when I'm filling in my information on the example, since I can see that x has the positive coefficient, I can say that a, in this case, is the 3 value from the square root of what's underneath that. And then b is going to be the other one, so the square root of 4 is equal to 2. So these are the only values that are used in the actual standard form of a hyperbola, but to do anything dealing with the foci, I do still need to find a c. So my formula is the a squared plus b squared is equal to c squared. And in this case, 9 plus 4 is 13, and then you're taking the square root of both sides, but the square root of 13 doesn't reduce, so I just have that c is equal to the square root of 13. Once you have all 5 of those values listed, I still like to start with the coordinate for the center, even though they didn't actually ask me for that. That's where everything's going to be added or subtracted to. So I'm still going to start off by saying that the center, and in this case, it's the coordinate hk, so 0, 0. Now I can go on to listing everything else. They next wanted to find the vertices. And for the vertices, that's the one that's based on the length of a, just like for the ellipse, same thing, use the distance a, and we need to add and subtract that from the center. Now, whether we add it to the x or the y coordinate, that again comes from where we found a. Since a is underneath x in this case, I'm going to be adding and subtracting that a value to the x coordinate of my center. So I can add and subtract 3, that would be 0 plus 3 and 0 minus 3, which is just plus or minus 3, comma 0. Or if you'd rather, you can write that out as the two different coordinates, 3, 0 and negative 3, 0. This is just kind of a lazy way of writing those two things out. And then for the last part of this example, they want us to state the locations of the foci. And just like for the ellipse, a and c always go in the same direction. So if a was being added to the x coordinate, then c will be added to the x coordinate as well. And sure enough, that's what we had on this one. So going back to the center, it was 0, 0, but I'm going to add and subtract c from the x coordinate. So again, I will have a plus or minus square root of 13, comma 0. And that's all that this example has asked us for. So next we're going to look at the process of drawing the graph of your own hyperbola given some of the information. And the first part on doing this is to identify the a and the b values. So from the center of your hyperbola, if you find that a is 2, for example, I would start from the center, go right 2, draw a dot, and then go left 2 and draw a dot. And then I would find what my b value is. If my b value was, let's say, 5, then b is going in the y direction for this example. So I would go up 5 from the center and down 5 from the center. And then you would just kind of draw a rectangular box passing through those coordinates. That's where they got this rectangular shape from. So use the distances for a and b in the appropriate x and y directions for whatever your hyperbola shows. And then what they've done next is they've drawn a line passing through the corners of those of your rectangle. The formula for the slope on those, it's going to be b over a for the one going this way and negative b over a for the one going this way. That doesn't often come into play. All that really matters is drawing that rough rectangular shape. And then the ones that have the a values, that's where your hyperbola touches. So I would ignore the dots I drew on top. My graph would actually be drawn in the left and right side for this particular example. So you want it to touch the a dots, not the b dots, and then have it get closer and closer to the asymptotes in either direction. So that's basically your process for drawing them. You can see an example shown down here as well, same thing, where they are showing you both the horizontal and the vertical versions of those. So let's walk through being able to match the graph with its appropriate equation first, and then we'll draw our own next. One thing to note on this one is since the hyperbola is going up and down, that means it has to start with a y squared. It needs to be a positive y squared and a negative x squared. So right off the bat, I can eliminate this choice, and I can eliminate this choice. We need a positive y squared, which means usually they put y squared first. That's pretty standard. So in this case, I already have it down to two choices. Next, we could look at the center of the graph because this one seems to be centered at the origin, 0, 0. So I shouldn't see any numbers being added and subtracted from x and y. This one would be showing a center out at -3, +2. And my hyperbola is not centered around that location, so I can also eliminate that choice. But the other important information would have been what you see underneath. In the vertical direction, it should have been going square root of this number, so 2 up and 2 down from the center. And sure enough, if this was my center, it looks like it went up 2 for one vertex and down 2 for the other. And then if I was trying to draw in the box on my own, I would also be going right 3 and left 3. And that would give me the rough shape of the rectangle for my hyperbola here. And then you can see that drawing the diagonals through there, that does seem to match the shape of our hyperbola. So even if we weren't able to eliminate that one choice as easily, you can still see why it has to be choice B in this case. So now let's go through drawing the graph and labeling all of the information on our own. This one kind of combines everything you'll be looking for on a hyperbola. Well, first, let's talk about the coordinate for the center. That's always a good starting point for anything you're doing on these. Our starting point, we need to flip the sign on the numbers being subtracted from x and y. So it's going to be a -3 and a +1. And I'll go ahead and draw that dot as well. So left 3, up 1, that's the center of our graph. And that's just coming from the fact that my h value is equal to -3, my k value is equal to +1. And then since a is always the positive one, it's not the biggest one like it was for an ellipse, a is the positive one. So a in this case is 2, and b in this case is 3. And if we were trying to find things based on the foci, so I would have 4 plus 9 equals c squared. So this is the same as the other one we did. That means c is going to equal the square root of 13, because 4 plus 9 is 13, and then you take the square root of the other side. So now let's figure out the vertices and where they fall on the graph. My vertices in this case, my a value is 2, and since that a value came from the x variable, it's underneath x in this case, that means I need to add and subtract 2 to the x coordinate. So first, if you do -3 minus 2, you get -5, comma 1. And then for the other location, instead of subtracting 2 more, I'm going to add 2. So -3 plus 2 is -1, comma 1. So basically, I knew that from the center in the x direction, I need to go a length of 2 in both directions. So right 2 and left 2. Those are the locations of my vertices. It's in many ways easier to do graphically, and then just look at your graph and say, what coordinates did I just identify? -5, 1, and -1, 1. So that's kind of an easier way to check your work sometimes. Now, they didn't ask us for these other coordinates. The b value, that came from the y variable. So from the center, I need to go up 3, and I need to go down 3. There's no name for these coordinates. It's not something that you're going to be listing out because the foci are actually still going to be to the left and to the right of our vertices. But it is still important to draw those in because, like I said, we want to kind of do a light box graph passing through all those dots we just identified. This is not part of the shape itself. It just helps us figure out the shape of the graph. And then we have asymptotes passing through the corners of this rectangular box. And your last step to actually drawing in the hyperbola on your own is you need to make sure you're careful about using the dots on the top or the dots on the side. Top and bottom dots or the side dots. And that's based on which ones are actually your vertices. Since our hyperbola is going left and right in this case, because the a value came from x, that means I need to be using the ones on the left and the right hand side. So I'm just going to start from where I was touching the box and then extend out closer and closer to the asymptote on either side. And then I have this over here as well. I know it kind of goes off my graph, but that's okay. You can still see the shape of the graph here. So we now have a graph drawn in. The only other thing that we hadn't identified was the coordinates of the foci. And the foci always go in the same direction as the vertices. So we were adding and subtracting from the x-coordinate from that. So I'm going to do the same thing, but I'm using a different number this time. So starting from the center, which was -3, I'm going to add and subtract the square root of 13. Now, when we did the vertices, I did want you guys to write out the two different coordinates because you were able to evaluate -3 plus 2 and -3 minus 2. Those are numbers you can combine. But now that it's -3 plus square root of 13 and -3 minus square root of 13, those can't be combined because they are not like terms. One's inside of a radical and the other one is not. So it's acceptable to just leave it in this form. When they're both regular numbers that they don't have square roots on them, combine them. If one is a square root and the other one doesn't, then keep them separate. So that'll be it for the notes. That's it for graphing and identifying some of those most important features of the hyperbola.